Good evening, everyone, and welcome to York Observatory's Teletube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. Teletube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. And for any questions or comments you have about our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on Twitter with the handle at York Observatory and on Facebook at Alan I. Carswell Obs. I am Matt, and I'll be one of your hosts this evening, along with Maheen, Arfa, Rosayla, and Sergiy. Tonight, we've got a great presentation about the Earth. Yes, the Earth on Our Planet series. So, but before that, the observatory at York campus is in Toronto. And to welcome you to our show, we would like to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many indigenous nations. The area known as Toronto has been taken care of by the Anishinaabe Nation and the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many indigenous people. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts are but the very latest in a very long history of astronomy in this area. And before we get started with our main show, we want to give you a little update on what you can see this coming week. So we currently have Vega, Uranus, Altair, Betelgeuse, and Ceres in the night sky. And yes, we've already talked a lot about Vega during our teletubes, but what about Altair? Well, first things first. If you want to find Altair, you'll be able to see it in the constellation of Aquila, the eagle, where it will be the brightest star. And it is actually the 12th brightest star in the night sky. I know that doesn't sound like much, but taking account the actual number of stars in the night sky. So being the 12th of that becomes a very huge deal, right? Especially considering that it is located at 16.7 light years away from us. And it is only 1.8 times more massive than the sun. And well, Altair is also known to be one of the stars forming the summer triangle formed by Vega and Cygnus as well. It is called the summer triangle since it basically dominates the northern hemisphere during the summer, where it is very prominent. And as a matter of fact, it was actually used in military navigation before, having the name of the Navigator's Triangle. Another interesting object in the night sky at the moment is Ceres, which is the largest object in the asteroid belt, and it is considered to be a dwarf planet, the only one located in the inner solar system. Now, just to have some perspective of its size, Pluto is still 14 times more massive than Ceres. And well, Pluto is not that big. Its size can actually be compared to Russia. So imagine something 14 times smaller than that, 14 times smaller than Russia, as a dwarf planet. Quite interesting, isn't it? And if that's not cool enough for you, well, how about the fact that both Ceres and cereal come from the same root? Yes, the word for that thing we eat with milk for breakfast is actually named after the Roman goddess of corn and harvests, Ceres, just like the dwarf planet. Now, these are some cool, interesting facts about a dwarf planet, but what about our own planet? What about Earth? Well, if you were interested in learning more about your own planet, then this is the perfect teletube for you. So why don't we start from the beginning? Go ahead, Sergiy.
Thank you, Matt. The history of our home planet starts 4.5 billion years ago, defined by both heat and gravity. In 1944, the Russian geophysicist Otto Schmidt suggested that the formation of the Earth, as well as the other planets, was based on the gradual accretion of cosmic dust into a clump that got bigger and bigger. Due to the planet being constantly hit by other large objects, immense heat was produced that melted the cosmic dust in the interior. The magma ocean was the source of volcanoes for millions of years. The early history of Earth came from the discovery of zircons in Western Australia that were between 4.1 billion and 4.3 billion years old. The zircon crystals were important as they don't get dissolved during erosion, but are continually deposited in sediment, leading to them being able to survive for billions of years, recording for us the ancient history of the Earth. The early history of the Earth is when very important properties of the Earth, such some even necessary for life as we know it, developed, such as the differentiation of the planet, which caused layers to form on the Earth, with the densest in the center core. This caused Earth's magnetic field, shielding Earth's atmosphere from cosmic radiation. The main divisions of the Earth include the crust, the mantle, and the outer and inner cores. The crust can be divided into two different types, oceanic and continental crust. The sum of both make up less than 1% of Earth by mass. The mantle represents 68% of Earth's mass, whereas the core is mostly iron and makes up 31% of the mass of the Earth. The outer core is liquid, whereas the inner core is solid. Besides the famous layers of the Earth, some less well-known layers are the lithosphere and asthenosphere. The lithosphere is a combination of the Earth's crust and rigid solid part of the upper mantle. This is contrasted with the asthenosphere, which contains the molten upper mantle material that behaves plastically and can flow unlike the brittle material of the lithosphere. Another layer is called the moho, or the Mohorovičić discontinuity, named after the discoverer Croatian scientist Andrija Mohorovičić. The moho is the boundary between the crust and the mantle. The Earth's atmosphere can be said to reach from the surface of the Earth to around 10,000 kilometers above the surface, where it gradually blends into space, but the exact upper boundary is disputed. What is agreed upon by most scientists is that most of the atmosphere's mass, between approximately 75 to 80% of the entire atmosphere, is located up to a distance from the surface of around 8 to 15 kilometers. The chemical composition of the atmosphere is mostly nitrogen at 78%, oxygen at 21%, argon at 0.9%, and 0.1% of other gases, including carbon dioxide, methane, water vapor, and neon. The atmosphere can be divided into 5 layers, starting with the closest to Earth's surface. To the farthest is the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. The famous temperature variations of the atmosphere can be seen on the screen right now. The first one, the closest to the Earth's surface, the troposphere, comes from the combination of the Greek word tropos, which stands for turn, way, and manner, and the word for sphere. The troposphere extends to about 7 to 15 kilometers from the surface. This range exists since it is thicker at the equator and thinner at the poles. Most of the clouds in the sky are in the troposphere, which can be explained by the fact that most of the water vapor in the atmosphere is located there. You can also find most of the atmosphere's dust and ash particles in the troposphere. The higher you go, the colder it is. The second closest layer to the surface is the stratosphere, which comes from the Latin stratum, or a spread for bed, coverlet, quilt, blanket, a pillow, bolster, and a bed, and the word for sphere. The stratosphere reaches to an altitude of around 50 kilometers from the tropopause, or the top of the troposphere, where an increasing altitude is met with an increasing temperature. The stratosphere has a layer of high concentration of ozone, or O3, within it, which protects us from harmful solar ultraviolet radiation, which can cause both tans and cancer by absorbing it. This absorption is the reason it gets warmer the higher you go in the stratosphere. The third closest layer to the surface, the mesosphere, comes from the ancient Greek word mesos, or middle, and the word for sphere. The mesosphere reaches from the stratopause, the top of the stratosphere, up to around 85 kilometers. Just like the troposphere, the altitude and the temperature are inversely correlated. If one wants to find the coldest temperature in the atmosphere, they should search near the top of the mesosphere, where it is around minus 90 degrees Celsius. If you ever looked up in the sky and saw some memorable shooting stars, some of them could have been from meteors burning up in the mesosphere, as although the atmosphere is thin, it is still capable of causing meteors to burn up. The second farthest layer is the thermosphere, which comes from the ancient Greek word thermos, meaning warm or hot, and the word for sphere. The thermosphere reaches from the mesopause, no, not the word you're thinking of, to the thermopause, which is around 600 kilometers from the Earth's surface. The thermosphere is like the stratosphere, where temperature increases with altitude, but instead of the ozone layer, it is due to solar radiation, which can get to 2000 degrees Celsius in the upper regions of the thermosphere. It makes sense why the thermosphere comes from the word for hot. The farthest layer of the surface is the exosphere, comes from the ancient Greek exo, meaning outer or external, and the word for sphere. The exosphere can be considered a gradient of space where there is no distinct line between the two. The outermost layer is so far away from Earth that Earth's gravity is too weak from keeping molecules from escaping our planet. Next up, we have Arfa, who will tell us the components necessary for life.
Thank you, Sergey. Now, no one is certain how life actually started. However, we do have the idea of what were the important components that help life to exist on Earth. In order for life to exist on any planet, not only Earth, but there are 5 very important factors that help in the possibility of life. Temperature. Temperature plays a very important role in this situation. All living things are made up of molecules, and temperature influences on how quickly atoms and molecules move. Organisms are made up of protein structures which can be very temperature sensitive. Life seems to exist in a certain range of temperature ranging from -15 to 115 degrees Celsius. And out of all of our solar system, only on Earth's surface is this temperature range. If the temperature is too high, for example, over 125 degrees Celsius, our protein and carbohydrate molecules and DNA structures start to break, and at high temperature, the water will start evaporating from the cell structure. On the other hand, if temperature is too low, it causes the chemical to react slowly, or there won't be no reaction at all because every reactions require a certain activation energy level to start the reaction. Water. Water is known to be the biggest factor when searching for life on any other planet. Only Earth's surface has water in its solar system. Other solar planets have water stored either in the polar caps or used to have water in the past. Some might have oceans locked underneath their surface, for example, Europa. Water is essential for life as chemicals that cell needs are dissolved and transported in water and are circulated throughout the living organism. Water is also the key component of the process called photosynthesis. Energy. Just like water, energy is very important for the chemical reaction that occurs in cells like photosynthesis in plants. Earth is at a prime distance from the sun that not only the temperature is habitable for the planet, but the amount of energy received helps the organism run the chemical reactions to sustain life. Life is able to use light at levels less than 10 to 5 of the solar flux at Earth. Solar flux, or concentrated sunlight, is a measure of how much light energy is being radiated in a given area. If light energy is too much or the rays from the sun are too concentrated, like ultraviolet rays, it would damage the cells or even eradicate life from planet Earth. Atmosphere. Now, atmosphere plays an important role in existence of life. Atmosphere traps and heat shields to the surface from harmful radiation and provides chemicals needed for life, such as nitrogen and carbon dioxide. On Earth and Venus, out of the entire solar system, these are the planets that are the right size to hold a sufficient sized atmosphere, but Earth's atmosphere is about 100 miles thick. It not only keeps the surface warm and protected from the radiation of the sun, but it also protects from small and medium-sized meteorites. Nutrients. Talking about nutrients doesn't only mean the elements, but also the active circulation of the planet. Now, just talking about the nutrients right now, only Earth is made up of the compounds such as carbon, nitrogen, hydrogen, and oxygen that exist together. Over time, an interaction of these molecules and elements resulted in molecules that became the building blocks of life, such as sugar, enzymes, protein, and DNA. After the presence of all these nutrients, the main part was the circulation. The planet Earth's transportation and replenishment of these nutrients through the surface of the Earth is volcanic system and water cycle that are active in the perfect ratio and that help Earth sustain life on. But on the other hand, like other planets or moons, for example, Jupiter's moon in this case, the deep volcanic system is too active, due to which it's hard for life to exist in such system. The summary in all is that the planet Earth did not have these nutrients or the transportation system of these nutrients. Life could not have existed on this planet. Now, these were the five most important building blocks of life on planet Earth, but of course, there are many other components that help sustain life. Each of these components have an immense role in the formation of life, and even if one of them was more or less, life might not have existed on planet Earth. Now, on to the significance of the moon. The moon has a lot of effects on planet Earth. Although it is almost 50 times smaller than Earth, it causes a lot of changes on this planet, starting with the most common one, tides. Tides are caused by the gravitational pull of the moon and affect Earth in many ways. Tides can be used to generate energy or help in fishing, but it also makes our day longer. Yes, due to the moon gravitational pull, we have 24 hours long day. Moon is moving away from planet Earth, due to which Earth's spinning is getting slower. Also, the moon is one of the reasons for the tilt of Earth on its axis, and therefore we have different seasons. Last but not the least, our nights will be much more darker if we didn't have moon. Now on to Maheen.
Thank you, Arfa. Earth, our home planet, is the third planet from the Sun. The inner four planets of the solar system are called terrestrial planets since they are smaller, solid, and Earth-like. Earth orbits at an average distance of about 93 million miles from the Sun, meaning that it takes about 8 minutes for the sunlight to arrive. As you move outward from the Sun, the planets are spaced increasingly farther apart. Jupiter is about 5 times as far from the Sun as Earth, while Neptune is some 30 times farther. Earth's position in the solar system's roughly disk-like arrangement has a big role in it being habitable. Earth's position in the solar system, as well as the speed with which it rotates, results in 24-hour Earth days, night and day, and time zones. The reason being the gravitational pull of each planet, which affects the spin and rotation of other planets as well as of Earth's. The gravity of the Sun keeps Earth and every other planet in its orbit. If the Sun wasn't perpendicular in position to the Earth would travel in a straight line rather than an elliptical orbit. Earth's orbit is one of the major reasons for life on the planet. If it was not pulled into orbit by the Sun, it would eventually hit another planet or object in space and get destroyed. Earth is a very special planet. It has plate tectonics, liquid water, and an atmosphere that shelters it from the bursts of sun's rays. The most special feature of Earth is actually us. Quote, "It's the only planet we know of that has life," unquote, said Alan Boss, a planet formation theorist at the Carnegie Institute of Washington in Washington, D.C. Even though other bodies in the solar system, such as Mars or Saturn's moon Titan, might be leading towards evidence of either some form of life in the past or in the future, Earth is still the only world known to support life. Earth hosts not just life, but intelligent life, which makes it very unique. Quote, "The Earth is remarkable for its precisely tuned amount of water, not too much to cover the mountains and not so little that it's a dry desert, as are Mars and Venus, our sister planets," said Geoffrey Marcy, an astronomer at the University of California, Berkeley. The fact that the water on Earth has remained liquid for so long is astonishing. It didn't freeze or fry like water on other planets. Earth's position being just right has helped it to have such distinguishing features. Another just right aspect of Earth is its size. If it was much smaller, it wouldn't be able to hold on to our precious atmosphere. And if it was much larger, it might be a gas giant too hot for life. The moon plays an important role when it comes to life on Earth as well. It helps stabilize the planet's rotation. Earth is the fifth largest planet in the solar system. It is smaller than the 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, but larger than the 3 other rocky planets, Mercury, Mars, and Venus. Earth is most comparable to the terrestrial planets and very different from the Jovian planets. Terrestrial planets are much different from giants In addition to being much smaller, they are primarily composed of metals and rocks. They are made up of elements which are less common in the universe as a whole. The most common metal is iron, and the most abundant rocks are silicates, which are made of silicon and oxygen. Earth, Mars, and Venus have roughly similar bulk compositions in comparison to Mercury, which has the greatest proportion of metals, and Moon, which has the lowest. Generally, farther a planet or moon is from the sun, the cooler its surface. In addition to the sun, however, the surface temperature of a planet can be influenced by its atmosphere. Without the atmospheric insulation due to greenhouse effect, the oceans on Earth would be permanently frozen. Earth's average temperature is between 14 to 16 degrees Celsius, but it can go as high as 56.7 degrees Celsius and as low as minus 89.3 degrees Celsius. The variation of temperature is due to the different seasons we experience. Seasons on Earth are due to its elliptical orbit around the sun and its tilt. Venus is one of the extreme examples where its thick atmosphere of carbon dioxide acts as an insulation, reducing the escape of heat buildup at the surface, resulting in a temperature greater than that of Mercury. Mars has a temperature generally below freezing, with air being very thin. It is so dry that it has not had any rain for billions of years. The outer layer of the Jovian planets are neither warm enough nor solid enough for human habitation. All this suggests that there is no place like home. Next comes the future of our home planet Earth, which Rosayla will cover.
Thank you, Maheen. The near future of Earth is greatly determined by humanity's actions in the next few decades. As greenhouse gases in the atmosphere continue to increase, not only does the overall climate of Earth change, but the geology changes as well. These changes may even be visible within our lifetimes. Among the first changes would be temperature increase and its consequences. By the year 2100, temperatures are expected to increase between 1.4 to 4.7 degrees Celsius from our current global averages. The increased temperature would lead to changes in weather patterns and a reduction in ice cover, both of which result in rising sea levels. Sea levels are expected to rise 0.3 to 1.2 meters, which would lead to changes in weather patterns that depend on ocean temperatures and an increase in ocean acidity. The weather patterns of Earth would change with more water being able to move throughout the water cycle as a result of increased ocean evaporation. Within the next century, more extreme weather patterns, including those created by the El Niño Southern Oscillation and the Atlantic Multi-Decadal Oscillation, are expected to be seen. Despite these patterns being natural phenomena of the Earth, they would still be affected by this change. Finally, with a large portion of Earth's ice cover gone, an ice-albedo feedback loop would be created. Ice is more reflective than Earth's surface, and as such, when ice cover decreases, more of Earth's rocky crust will be exposed, thus increasing the amount of radiation absorbed by the Earth. An increase in radiation absorbed leads to more increases in temperature, and so the cycle repeats. These, however, are only the changes influenced by humans. Earth's natural changes will take place over millions of years. The changes that will take place are similar to those that helped shape the planet 4.5 billion years ago. Many volcanic eruptions will occur that will result in the eventual cooling of Earth's surface. Aerosols launched into the stratosphere can remain for many years, causing cooling by fractions of a degree, whereas aerosols that only remain in the troposphere do not have as harsh of an effect. Outside of volcanic eruptions and human activity, the Earth will remain the same for another 200 million years, where another supercontinent will form, Pangaea Ultima. This supercontinent will be similar to Rodinia, which formed about 1 billion years ago, then broke up around 700 million years ago, and supercontinent Pangaea, which formed around 335 million years ago and remained a supercontinent for 115 million years. In the far future, the sun will be the main influencer of Earth's future. One of the many influences the sun has over the Earth is the changes in its output. Measurements of the sun's output, specifically solar irradiance, were not measurable until the 1970s with satellites. Prior to that, sunspots were used to get a rough estimate of solar activity. Solar irradiance can vary about 1.4 watts per square meter, which is about 0.1% of the usual 1,366 watts per square meter. Solar irradiance fluctuates on an 11-year cycle with entirely different changes over a longer period of time. The changes in irradiance are measured by carbon-14 and beryllium-10 isotopes that are formed when cosmic rays interact with Earth's atmosphere. This variation, along with photochemical reactions in Earth's stratosphere, are responsible for changes in temperature as the altitude increases. Earth's orbit will also change and affect the planet as a whole. Some of the factors that are associated with Earth's orbit are the precession of equinoxes, which is a change in the timing of seasons that happens on a 26,000-year cycle, the change in the tilt of Earth's rotational axis, which is on a 41,000-year cycle, and the amount Earth's orbit deviates from a perfect circle, which is on a 100,000-year cycle. The three variables mentioned affect the amount of solar radiation different surfaces of the planet are exposed to. They all had a role in the last ice age, but have had no recent impact. Finally, the most influential cosmic event on the Earth is the future expansion of the Sun. The Sun has been fusing hydrogen in its core for around 4.6 billion years. As this fusion process continues, the temperature and density in the core of the Sun will increase, as does its brightness. Every billion years, the Sun increases in brightness by around 10%. As the Sun's brightness increases, the temperature increases proportionally. This increase in brightness will continue as long as the Sun contains hydrogen in its core. Following this pattern, the Sun will reach uninhabitable levels of brightness after around 6.5 billion years, where the brightness will rise to 2.2 times that of the Sun currently. Earth's magnetic field and atmosphere will no longer be able to protect the Earth at this point, and any remains of life will no longer be able to inhabit the planet. After around 7.1 billion years, the Sun will expand since the weight of the star has grown as it has continued to fuse hydrogen, and it will continue fusing helium, and so on. In terms of brightness, 500 million years after its expansion, it will be 34 times as bright as the Sun currently. Another 45 million years after that, it will be 105 times the brightness. And 40 million years after that, it will be 2,300 times as bright as our Sun. At this point, the Sun is considered a red giant. The Sun will have expanded to engulf Mercury, Venus, and possibly even Earth. This is where the future of the Earth will end, as the habitable zones are now near the orbits of Jupiter and Saturn, as far as our solar system is concerned. Well, everyone, you've been listening to the Alan I. Carswell Observatory's weekly Teletube broadcast, the astronomy and astrophysics program written by and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Sergiy, Arfa, Maheen, Matt, and myself, Rosayla. Make sure to leave any comments or questions in the comments section of the video and talk to us in the chat right now. We will be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to make a donation, see our website at observatory.info.yorku.ca. You can always connect with us on Twitter with the handle @YorkObservatory, and check out our website for show notes, content updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.